see everyone.
All right, how's it going? My name's Reid.
I'm Sam.
I'm Ford. And I'm Salman.
And back in 1969, Purdue University's very own Neil Armstrong first set foot on the moon. And so Team 11 put together a toy that was inspired by not only this event, but over 150 years of impressive steps forward for Purdue University graduates. And so this is what we came up with. Yeah, so just some background while this video. This toy design was made for girls and boys aged between 5 and 8 years old. We designed it so that it would come in a kit and they could assemble it. We were able to build it for about $18, which was pretty impressive. Needless to say, we didn't have to have all the 3D printers and stuff. So then we could sell it for the same cost as a Lego of the same size that they could be able to put together, assemble, feel really proud about when they mechanically drove it. So let's kind of start talking about where we got our inspiration from. There's this awesome Disney mechanism YouTube that you guys should watch the full thing, where they create really cool actions based on mechanisms, turning angular motion into linear motion and so on. So we wanted to replicate this, and you can go to the next slide. We wanted to replicate this type of motion and create an astronaut that would leap across the moon. So what we did was we kind of came up with some ideas, sketched it out on paper. We wanted it to look sort of like this, and then we'd have this mechanism box underneath which would hold all the parts that would create this motion. And then we also added a lunar module that rotates in the background as if it was taking off. So next slide.
So what we did for the CAD of the astronaut was we found an STL file which was open source, and then quite heavily edited it. We had to take apart the different joints and remove the supports, and then we printed the joints separately from one another and attached them into the assembly that you see here. And then the lunar lander was a similar situation, open source, and we made small changes so that it would fit on our model and move the way we wanted it to.
And so here's a basic assembly of our toy. And at the moment, it currently does not have an animation to it, but we are working on that for the final toy presentation next Monday. And so what you see here is rods connecting the arms and the legs to a hidden crankshaft inside the box. And on the right side, right face of the box, you see a red lever. And you turn that lever, turns the crankshaft, moves the rods. The astronaut is animated like he's walking on the moon. And at the same time, the lunar rover in the background is spinning. So this led us to, well, once we finally had everything modeled, we went to 3D printing. We did the lunar lander with SLA, and we did a few other parts with SLA 3D printing. And once we ran out of the volumetric limit on that, we used FDM to do the astronaut parts. In addition, we used laser cutting for the box that houses the crankshaft. We decided to use plywood, 1/4-inch plywood for the top and the bottom, and then for the sides to use clear acrylic so that you can see the crankshaft and see how it moves. Also kind of give the kids who play with this an inspiration for mechanical devices.
So we'll talk a little bit about the mechanisms. First, really quickly, so the way you have an input source, which is the user or the child, who rotates the handle or disc, which is on the outside of the box. That in turn rotates a crankshaft. So the way we designed it here is the two inner cranks here. Those control the arms. So when you walk, you have opposite strides. So we wanted the arms in the on opposite directions. These two in the middle, and then the two on the outside operate the legs. And obviously, when you walk, your legs are in different strides, so they're going to be completely opposite one another. So then based on that rotation about the center, It moves almost like a piston in a car, up and down, which then moves the arms and legs in a skipping motion. Now, then that crankshaft is also connected to, what's it called, a pulley system. The pulley system then rotates one of these gears, translates the angular motion 90 degrees, and then in turn rotates the lunar module at the top. Just to show you, I used SolidWorks a little bit to help visualize and adjust these lengths so I could figure out the proper radius, and it moves in that action. Next, we're going to talk a little bit more about the skeleton model.
Right, so as we were learning in class how to make skeleton models, we decided it would be a good way to model our mechanism, figure out all the joint lengths, and then adjust them as needed as we continue to make updates to the prototype. So we made a complete skeleton model. We put in all the joints and connectors between them. It's a three-dimensional skeleton, which also has working mechanisms for a cam follower, for the slider joints, for the bevel gears, and for the pulleys. We are facing some issues with this model. We realized that with Creo, once you start assigning bodies, you can't go back and change sketches without deleting the bodies. Because of that, it's very hard to make changes. We decided to get rid of our cam follower, but we realized we couldn't update the model to reflect that. So because of that, we're going to move towards a normal CAD assembly for our final model that we submit. But we have made the skeleton model, and we used it to help figure out how all the joints would connect and what lengths to use and whatnot. So it was a pretty useful skeleton model. And then what we have so far is we have a prototype that looks pretty good. It's got everything assembled. And as you can see, we've got painted and designed and printed. We have everything there. The crankshaft is attached. We have 4 slider mechanisms, the pulleys set up as well, and the bevel gears. The current work that we have left is we need to finesse the joints. They're pretty stiff right now. There's more friction than anticipated on the sliders, and the lengths are a bit tight. So we need to work on that, work on adjusting them so that it properly flows smoothly when you rotate the handle. And we also need to optimize the pulley system. It tends to slip a bit, so we're just going to experiment with different bands, and we're going to maybe add a support to the pulley joint just so that it manages torque well. And once we have both of those down, we should have a smoothly functioning model. Yeah, thank you. Any questions?
While we take questions, Sam will walk around and just so you can look inside.
Question over there. So when you're figuring out the medium length, did you just go and did you have to calculate how much it's gonna move with that, or did you just try and error?
So what we actually ended up doing was that we have a slider. So the foot is connected to a dowel rod. All the limbs are connected to dowel rods, but they're not rigid joints, they're sliders. So we put full length dowel rods and we connected everything, and then we cut them down to the maximum length needed. So it's actually a dynamic length, and adding that degree of freedom means that our machine is less likely to get stuck when we're rotating it, because it's got more degrees of freedom than you need.
You mentioned that you use the skeleton model and you cannot go back to change the sketch dimensions.
So we can change the sketch dimensions, but we can't change some of the types of joints. We can't turn our slider into a pin joint or into a normal fixture without deleting the bodies and then making them again and redefining every single mechanism or every single joint.
You can redefine it very also.
Well, it wasn't giving us the option, and it was. I mean, we can have a look at it, but it was definitely being very unreasonable.
Do you think what's the main reason for this current projection?
I think there's so much friction on it.
We think
I think there's just so much friction on it, and
it's not a design issue.
we have a skeleton model which works. So theoretically, it should be working. And we did all the machine design just based on but it's a very complex mechanism, and so if there's angles off, if there's a little bit of an angle
If you take the camshaft off, can you rotate here to get the the trolley work?
Oh yeah, without the astronaut on it, it'll do like a. What was the
No,
question?
I'm talking about this rotation. If
Oh,
there is
yeah.
no shaft, no camshaft here, by rotating this,
Mm-hmm.
Yeah. So
actually
Yeah.
will it be able to rotate here?
Yeah, so
Yeah,
we
so
actually
that does
put
rotate.
the astronaut on last, and we were able to get this to spin.
Okay,
Yeah.
as long as this shaft can spin this,
Yeah.
this
Right,
portion of it.
exactly.
So what you need to fix is this here.
Yeah.
We need to fix the crankshaft. So the lunar module does spin
Okay.
when it's not connected to the astronaut. It just all the tolerances and stuff are it's a lot of moving parts, and so and a lot of friction.
Okay.
Yeah.
Still
But-
control.
Yeah,
Okay.
yeah. Thank you for bearing with us. All right.